Hi everyone, welcome to this session. So we will be solving this interesting interview question, and this question can be asked for your online assessment as well. Okay, so let's start. So this is a op-amp based circuit. We all can see, right? So actually, so there is a switch, and that is the important thing for this particular problem. Okay, so we can see there is a switch. Okay, so this is the switch, and when the switch is like when this s, let's say this is s. Okay, when this s is 0, the switch is closed. Okay, and when the switch is 1, then like this is the waveform. Okay, this is the waveform. So when this is 1, then the switch is open, and when this is 0, the switch is closed. Okay, so basically this is the second case, like the case b. Okay, when this waveform will comes into the picture, and for our first case the s is always 0. Okay, so s is always 0 means the switch is always closed. Okay, then if the switch is always closed, then what will be our equivalent picture? And one thing, so let me check the things. So our vdd is at 15 volt, vss is 0 volt. Our v in and v1 and v2 are given as like that. Okay, and this is the ideal op amp. Okay, this is the ideal op amp. ideal op amp Ideal op amp. Okay, so now we will be solving the first case. Okay, and we have to find the vx, vy and vout. Okay, so this node voltage, this node voltage, and this node voltage with respect to ground, we have to find. Okay, we have to find. Now for first case, we can see for case number 1, the switch is like s is always 0, that means the switch is always closed. So what will be our equivalent picture? So if I draw the equivalent picture, so it will be looking like this. Okay, so so this is closed, so this will be short circuit, right? Then we have, so if we short circuit this, right, so this will be a normal short circuit. So 5 ohm resistance is like not contributing anything to the circuit, right? There is v1, so upper side is positive, lower side is negative. This is v1, this is v2, right? And we have feedback from the both inverting and non-inverting terminal, right? This is the thing. And we have V out and 1 ohm, 1 ohm, 1 ohm and 5 ohm, right? So 1 ohm, 1 ohm, 1 ohm and 5 ohm. Okay, so basically, so if we can see that, like we have V out from here, right? And we have two type of feedback present here, but to 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 act to act as an amplifier, the op amp like should be only one type of feedback should be present there. Okay, so to find positive feedback, so then the the feedback factor to the positive terminal, like the node voltage to the positive terminal, should be greater than the negative terminal voltage. Okay, if this is a positive feedback. Okay, and if this is a negative feedback, then the negative terminal potential must be greater than the the negative terminal potential must be greater than the positive terminal potential of this op amp. Okay, so basically we need to check the feedback factor from this V out to this node, and from V out to this node. Okay, we have to find the feedback factor, and which if this feedback factor is dominant, then it will be a negative feedback circuit. And actually they are like, this should be a negative feedback circuit as well. Okay, so that it can act as amplifier, right? So now, so let's see which, like we have to check first, like there is positive feedback or negative feedback present there. Okay, so let's say this is V negative and this is V positive. Then what will be the feedback factor from this negative terminal? So let's say positive feedback factor to the negative terminal. So this will be nothing but 5 divided by 5 plus 1, right? So this will be nothing but a resistive divider from here to there, right? For this negative, for this beta of this negative terminal. So this will be nothing but 5 by 6. Now what will be the like the positive feedback factor at positive terminal? So this will be nothing but so this will be 1 divided by 1 plus 1. So this is half. So we can see that this negative, so this implies that the feedback factor at this negative terminal for this negative terminal is greater than the feedback factor at the positive terminal. Okay, so this implies that there is a negative feedback present. Okay, so circuit, the op amp is in negative feedback. Okay, so now for negative feedback, the problem becomes easy because this is a ideal op amp. Okay, ideal op amp, and there is a negative feedback present, so we can directly use virtual short concept, right? Virtual short concept. Okay, that means the positive terminal voltage is equal to the negative terminal voltage. So actually we can see that here Vx and Vy are the positive and negative terminal voltages. So we can say that this will be nothing but Vx is equal to Vy. Okay, so this is the thing. So we are using the virtual short concept as there present a negative feedback. Okay, so here in this case, so we can see that like this implies is that this, okay, let me check. So this implies is that here the V negative voltage is greater than V positive voltage. Okay, now so we have to check that. So these two voltage are equal. So if I can copy the circuit, okay, so the circuit is that, right? So now so we can see, so this will be our V out and this will be on off. So this node voltage equal to this node voltage. Okay, now we have to do some KCL and KVL. Okay, so actually no current can go through this branch, so all of the current has to flow through this branch, right? Okay, so now we can, if we write a KCL in this branch, so this will be nothing but V1 minus V, let's say Vx, okay, divided by 1 ohm will be nothing but equal to Vx minus V out divided by 1 ohm. Okay, so this implies is that, so it will be so V1 plus V out will be equal to Vx, right? And if I do the same thing for this branch, so this will be, so let's say this is the expression 1. Okay, and the expression 2 will be, so V2 minus Vy and Vx equal to Vy, right, divided by 5 will be equal to Vy minus V out will be equal by 1. So this will be what we will get. So let's say V2 minus Vy, 5 Vy minus V out. Now we have to just solve this two equation. Okay, so V2 plus V out will be 6 Vy. Okay, now we have seen that Vx will be equal to Vy. So let's say this is so we can put this value. So let's say this is equation 2. So now so here, so we have to need V1 and V2. So let's see what are the value. So we can see V1 is 12 and V2 is 10. So V1 is 12 volt and this is 10 volt, right? So now if I do some calculations, okay, so from this equation, this will be 10 plus V out will be equal to 6 Vy, and from this equation 12 plus V out will be equal to 2 Vy, right, as V equals Vx, right? So now if I do equation 1 minus equation 2, okay, so 1 minus 2, so it will be nothing but, so this will cancels, right? So this will be minus 2 will be equal to uh, so 4 Vy, right? Am I doing like something wrong? In, okay, let me check. Okay, oh, let me check. Okay, so V1 and the switch is closed, right? S0 means 0 means switch is closed, so there will be no 5 kilo ohm resistance. Okay, and okay, yes, okay. So here is negative feedback, so we can use that. So V1 minus V positive, V1 minus V positive. Yes, so this current and Vx minus V out will be same current. Okay, so this is thing, these things are okay, and we have V1 plus this is Vx. Okay, and V2 minus Vy by 5 will be equal to Vy minus, yes, this is okay. So this is 5 V out, right? So there was a mistake, right? So this will be 5, right? Now, so this will be 5 as well. Okay, so okay, so now we need to, okay, so let multiply the equation, uh, like we can multiply right like that, right? So this will be 6, right? So okay, this is V out, so this will be 3 V out, and this will be into 3, right? Now if I do the uh, like if I do these things, okay, 1 minus 2, so this will be, so this will be, so this cancels, right? So this will be, so 10 minus 36 plus 5V out minus 3V out. Okay, it will be equal to 0, right? Now we can see, so this will be 26 will be equal to 2V out, right? So V out will be 13 volt. Okay, so V out will be 13 volt. Now what will be the Vx? Let's say Vx. So Vx is nothing but, so Vx is nothing but, let put this equation. Okay, so Vx is nothing but V1 plus V naught by 2, right? So V1 plus V out by 2. So this will be 12 plus 13 by 2, right? So this will be 12.5. Okay, so this is the case one. Okay, so now we have found that for this case Vx equals Vy equals 12.5 volt, and V out is nothing but 13 volt. Okay, so this is the first answer of this option A. Okay, now we have to check this case. Okay, so S0 means the switch is closed. Okay, there the switch is short circuited, and F is on means the switch is open circuit. Okay, so let me do the things again. Okay, so this was our waveform, right? So this is 1 and this is 0. So for this time duration, and let's say this is Tx. Okay, so for this time duration the switch is closed, right? So let me draw the waveforms here. Okay, so we have seen that this, let's say this is Vx, let's say this is V, let's say this is time, right? Let's say this is Vy, and this, let's say this is V out. Okay, so I am writing all of the waveforms. Okay, so we have already seen that when S is 0, so this is S is 0, right? S is 0, and here S is 1. So when S is 0, we can see this type of voltage, right? Where I have written, so this is the like Vx equal, like Vx equal Vy equals 12.5 and V out is 30, right? So we can plot the waveform accordingly, right? So now if I plot that, so let's see, this is Tx. So you can see that this is 13 volt. Okay, output 13 volt, and Vx equals Vy is 12.5 volt. 12.5. Now S is 1. Okay, S is on means the switch is open. Okay, so let me let me okay, let me draw the picture again. Okay, so now, so this was 5 ohm, 1 ohm, 5 ohm. This is 1 ohm and this is 1 ohm, and circuit is in negative feedback, so there is no any issue, not any issue, right? So this is 1, this is 1, this is 5, and let's say this was V1, right? This is 12 volt and this is V2 is this is 10 volt, right? So actually if the switch where is the picture? So if the switch is open, right, if the switch is open, so this 5 ohm resistance comes into the picture and series with this, right? So actually this comes in series, so we can write as a 6 ohm resistance, right? So let me so we can write as a this whole as a 6 ohm resistance, right? Now similarly we have to make some equation and calculate that. Okay, and one thing I want to tell at the last, please see the things. Okay, see the calculations. Okay, so if I do that, so 12 minus, so this will be the same case, right? Okay, now we have to check the feedback again, right? Like, is there is any positive feedback or any negative feedback present there or not, right? So now, so we have to check the feedback factor again, right? So what is the feedback factor now? So this is 6 ohm. So P plus will be nothing but 6 by, so actually we are making this node voltage with respect to V out. Okay, and while we calculating the beta factor, this input are inactive. Okay, so this will be AC grounded, right? For this voltage source, like this will be short circuit and this will be grounded, right? So now for feedback factor, this will be nothing but 6 by 6 plus 1, so this will be 6 by 7. Okay, and B negative is nothing but 5 by 5 plus 1. Okay, so this will be 5 by 6. Now which quantity is large, so you have to calculate that. So this will be nothing but 8 0.8 8. So this will be nothing but, so let's say this will be so 40 means 7 5, right? So this will be this, so and this will be 0.8, this will be 3. So what we can see, so this will be like that, right? So now we can see the positive uh, feedback factor is dominant. Okay, basically this becomes a positive feedback circuit. Okay, so we cannot apply the virtual ground short concept here. Okay, as though the op amp is ideal, we cannot apply the virtual short ground concept because the circuit is in positive feedback. Okay, so here is positive feedback. So positive feedback means it cannot as a acts as a amplifier, right? It is like as a oscillator, right? So it will normally check, like if this voltage is high, right, then it will go to the VDD, right? And like with respect to this voltage, right, let's say V positive and V negative, then and if this voltage goes high with respect to this, then the output goes ground, right, like the minus VSS. Okay, so now we have to check that. So now, so what will be the, like we can do the we can do KVL anytime, right? Now if I do that, so okay, so this become positive feedback. Okay, so that is for sure. Now so calculate, we have to calculate these two node voltages, right? So now so we can apply KCL anytime, right? So 12 volt 12 volt minus V positive divided by 6 will be equal to V positive minus V out by 1, right? So this will be an equation. Okay, and second equation will be 10 minus V negative divided by 5 will be equal to V negative minus V out by 1, I guess, right? So yes, this will be 1. So now how to calculate these two voltages? So we have previously find that V out was how much? 13 volt, right? So the initial condition of the V out is 13 volt, we can assume. Okay. So now to put V naught equals 13 volt. Okay. So for this case, I will get, like we will get, so this will be 12 minus V positive will be equal to V positive minus 13, right? So this will be 12 plus 13 will be equal to 2 volt, like 2V plus, right? Now V plus will be equal to 12.5 volt. Okay. Am I, yes, 12.5 volt. Okay. Now if I do the same thing here, okay, let me check once. Okay. Okay, so from here we can, directly assume that as the positive terminal node voltage is high, so the output will reach to plus VDD. Okay, so this is the thing. Okay, so we are not going to do that. Okay, not going to do this type of thing. So actually the V positive will be VDD. Okay, so this will be nothing but 15 volt. Okay, as this is a positive feedback circuit. Okay, so now we have to solve this as 15 volt. Okay, the output reach to, like the output gets saturated to 15 volt. Okay, so this will be 15. Okay, so this will be 15. Okay, as our V positive is high. Okay, so output will reach to VDD, like it will get saturated to the like plus VDD. Okay, so this will be 15, so this is 27, right? So 13.5. Okay, yes, this is the thing, 13.5. So V positive will be 13.5 and this is nothing but our Vx. Okay, now uh, what about our V negative or Vy? So again similarly we can find that. So 10 minus V minus will be equal to 5V minus minus 5 into 15, right? So this will be, so 10 minus 75 will be equal to 6V minus. Okay, so this will be 65 by 6. So this will be V minus and this is nothing but Vy. Okay, so this will be almost I'm doing something wrong. So okay, so this will be plus, right? So here will be plus, so this will be 85. So this will be 1, so it will be almost equals like that, right? Yes, yes, this is almost equal that. Okay, so this will be like that. Okay, so we have got this type of values, like the steady state of Vy will be 14.1 and steady state of out V plus or Vx will be 13.5 and the V out gets saturated when S is 1. Okay, so now if I draw the waveform, so here we can see there is no capacitor and no inductor, so the output or the node voltage can change instantly, right? Because all are resistive, right? Here the circuit is purely resistive, so the output waveform will jump suddenly from this node. Okay, like can jump. Okay, so now the output, so Vx suddenly jump to what? This is the 13.5, right? 13.5 volt, this voltage. Then Vy also jump to 14.1 volt, right? So this will be 14.1 volt. Okay, and V out gets saturated to plus 15 volt. Okay, so this is the final waveform and this is a very very good question, like according to me. Okay, so this will be the final waveform. Okay, so the trick is like the catch up is like if the positive, like the positive feedback is dominant, then the output is get saturated to the plus VDD. Okay, okay, so this is the thing. So we cannot apply the like the virtual short concept is the circuit is in positive feedback. Okay, if the circuit in negative feedback and the ideal op amp, then we can use the like the virtual ground short concept and so on. So actually this is the circuit and the final waveform will be looking like this. Okay, final waveform will be looking like this. Okay, so this is the final waveform. Okay, so this is all for today, and please give your valuable feedback. Okay, thank you.